Welcome back to The Explainer. Today we're demystifying some seriously dense mathematical architecture behind decentralized exchanges. We're going to see exactly why transitioning from messy approximations to absolute integer truth is, well, it's the future of DeFi. Specifically, we're unpacking dossier number 19, Polar AMM Dynamics. We'll be contrasting the traditional Cartesian math we're all used to with a completely radical new approach. All right, here's our roadmap for today. First, the capital efficiency struggle. Second, Uniswap's logarithmic tick debt. Third, the polar AMM pivot. Fourth, Pell-Smith rational coordinates. Fifth, the gambler versus surveyor. And finally, liquidating the tick debt. Let's get right into it. Before we even touch on exchanges, we have to ask a killer question, one that totally challenges a fundamental assumption about our hardware. Do computers actually process exact math, or are they just guessing? I mean, when you ask a processor to do complex, non-discrete math, it intuitively feels like the machine calculates a perfect, exact answer, right? But beneath the surface, it heavily relies on hardware-level approximations. It's what researchers actually call the grand computational illusion. So keep this massive technical compromise in the back of your mind as we look at how multi-billion-dollar financial protocols are built right on top of these guessing machines. Section 1, the capital efficiency struggle. So the whole history of decentralized exchanges is basically defined by this continuous struggle to optimize capital. We're talking about the relentless quest to make every single deposited dollar actually work for you, rather than just sitting uselessly in a smart contract. Early models like Uniswap v2 distributed liquidity uniformly across literally an infinite price spectrum. And because of that, vast reserves were just sitting idle, completely untouched by traders. But then Uniswap v3 comes along and introduces a Cartesian framework. This segments that continuous price curve into finite boundaries, which allowed liquidity providers to concentrate their capital in very specific price ranges. It was a real game changer that massively boosted efficiency. Section 2, Uniswap's logarithmic tick debt. But here's the catch. By forcing fluid markets into these rigid boundaries, the protocol had to invent a way to track those segments on the blockchain. And to do this, Uniswap relies on what we call ticks. A tick is just a discrete price interval. It takes the infinite continuous space of potential market prices and chops it up into a discrete integer grid. So when the market price moves across one of these tick boundaries, the smart contract has to actively kick liquidity in or out to ensure nobody goes insolvent. And as you can imagine, that means constant, highly expensive computational work for the blockchain. Now, to map out this continuous space, Uniswap uses this exact formula, 1.0001 to the power of I. This logarithmically maps the price so that each tick increment corresponds to exactly a 1 basis point change. To track these boundaries, the price at any given tick index is defined by this geometric base. It guarantees uniform granularity across the whole price spectrum. Pretty elegant, right? But remember that computational illusion we talked about a minute ago? This is where it catches up to us. Because navigating this exact grid requires approximations from the processor's floating point unit, or FPU. And these FPU approximations cause severe gas spikes and numerical drift during high volatility. When the market is going crazy and crossing multiple ticks sequentially. When a massive trade shifts the price wildly, the contract has to cross multiple initialized boundaries, loading new tick data every single time. And since the Ethereum virtual machine doesn't handle floating point math natively, these calculations are incredibly heavy. It leaves the pool vulnerable to rounding errors and nasty exploits like dust grinding. Section 3, the polar AMM pivot. This brings us to a massive conceptual leap. We are pivoting away from those Cartesian grids and moving towards non-Euclidean circular manifolds. We're fundamentally throwing out the standard XY graph and totally rethinking the geometry of trading. The lens polar AMM draws mathematical inspiration from physical gradient index lenses to focus liquidity omnidirectionally. Think of physical optics, like a Lüneburg lens seamlessly bending physical waves toward a single focal point. Lens applies that exact concept to DeFi. Instead of a Cartesian hyperbola, liquidity is mapped onto a circular manifold, concentrating depth perfectly around a target price peak. This is absolutely ideal for things like stablecoin pairs because it dramatically reduces slippage right where the price naturally wants to sit. But wait, we hit a massive computational bottleneck here. How on earth do you execute trigonometric curves in the EVM without relying on expensive, lossy floating point math? Moving along a circular curve usually requires sine and cosine functions. Trying to do that on-chain with standard approximations like Taylor series or Cordic algorithms, that's practically financial suicide when it comes to gas costs. Section 4. Pell-Smith rational coordinates. The climax of our explainer arrives with a truly elegant solution to this mathematical barrier. By mapping circular geometry into these Pell-Smith rational coordinates, Lens perfectly replaces continuous trigonometric angles with exact division-free integer mathematics. Using principles derived from Pell's equations and Chebyshev polynomials, Lens replaces those messy approximations with an exact rational coordinate ring. You really don't need to be a math PhD to appreciate what this means. Any integer solution corresponds to a perfect rotation. No divisions, no square roots, just clean, exact, unbelievably cheap math. Section 5, the Gambler versus Surveyor. To truly grasp why this shift is so revolutionary, we need to personify the hardware a bit. Think of it as a battle over how a machine observes and records the truth. On one side, we have the floating point unit. It's a fast but lossy gambler, just recklessly throwing darts. It uses secret proprietary seed tables baked into the chips to make incredibly fast but ultimately approximate guesses. On the other side, the arithmetic logic unit is a strict, slow and steady surveyor, dealing only in absolute, verifiable truths. The ALU surveyor absolutely refuses to guess. In its world, 1 + 1 is exactly 2 every single time. And that truth is firmly set across every single machine on Earth. So the crucial takeaway here is that Uniswap's reliance on the FPU Gambler creates what researchers call the wood chipper effect. It permanently mangles the data's exact identity. Because it relies on approximations to map its logarithmic ticks, the observer complexity literally exceeds the hardware's exact register width. The true data is basically fed into a blender, creating this irreversible informational debt. You can't ever perfectly reverse engineer the math back to its exact original components once it's been approximated. Section 6. Liquidating the tick debt. Lens permanently liquidates this tick debt by shifting the core logic entirely over to the ALU Surveyor, aligning the software design perfectly with deterministic hardware. This is a profound philosophical shift, going from approximating a curve to physically possessing the absolute state. It's beautifully captured in this quote from the Lens architecture docs. Because Pell-Smith scaling uses exact integer identities, a concept called magnitude implicit addressing, which basically means the value itself contains its exact location, the machine isn't guessing where the liquidity is anymore. It absolutely knows. It possesses the exact mathematical state without any of that lossy observer debt. The end result of all this? It's staggering. Lens achieves bit-perfect, flat O1 gas efficiency, and it slashes energy consumption by 74 times, down to just 0.05 picojoules. Because the entire state transition is executed as a single matrix vector multiplication, there's no more of that expensive sequential curve crossing. And for multi-asset pools, Lens uses a matrix concept called the Smith normal form to effectively untangle the assets, separating them into clean 2D curves so they don't interfere with each other. It's an absolutely incredible leap in both security and efficiency. So I'll leave you with this final, provocative thought. Now that we finally possess absolute mathematical truth, what are you going to program it to do? When we stop relying on the FPU Gambler and start building our decentralized exchanges on the unyielding certainty of the ALU Surveyor, we don't just optimize capital, we establish a flawless foundation for the entire next era of digital physics. Thanks for joining me on this explainer. Keep exploring, and I'll see you next time.